Okay, so it's homework 9, problem 3. Okay, so I think we've discussed this yesterday, but I think it's still worth mentioning again, the difference between theta and theta C. Okay, so theta is your hydraulic residence time. Okay, and theta C is something known as the mean cell residence time. So I was just talking about the difference between theta and theta C. Okay, so what is the difference between them conceptually is that if you have a tank and you have water, you have liquid flowing through, the time the water takes inside to come out, that's theta. Sorry, that's theta, the hydraulic residence time. Okay, if you have biosolids in the solution, the time for them to come out is known as the mean cell residence time. The time it takes, the average time it takes for those particles to get out of the reactor. This is the difference between theta and theta C. Okay, it's very important. So when is theta equal to theta C? Okay, when there is no recycle. When is theta C become greater than theta? When there is recycle. When there is an abundant amount of recycle. So keep those things in mind.
Right? So when there's no recycle and we're using like the Monod-Knox equations, we can like theta and theta C.
Yeah, they cancel out. They cancel out. Okay. Yes, and that's what you will observe in this question. The question itself told you assume there is no recycle. So even though it gives you a hint that theta is equal to theta C, but when it says no recycle, this thing should come to your mind right away. Oh, theta is equal to theta C, and that's why I wanted to start with this to tell you the difference between them. Okay, so no recycle means those two cancel out. Simplifies the equation quite a lot.
Theta C will never be less than theta.
I mean, as long as if you have recycle, then it will be greater than the hydraulic. I can't imagine a scenario where theta C would become less than theta itself. Maybe if your concentration is very dilute. If your concentration of the recycle is very, very dilute, then I can imagine it being, or the concentration of biomass itself is very dilute, then I can imagine it being so.
So it would mean the solids leak faster than the water.
Right? Yeah, does not make any sense. No. Yeah, so I don't think it's an applicable equality to say that theta C is less than. No. Okay, so with that in mind, let's go over question. So question 3, I'm just looking at the question. So the first thing they ask you to do is to find the substrate concentration, right? SE, correct? They ask you to find the substrate. Yeah. So it's here, determine the effluent substrate concentration, all right? So whenever you see that, the first equation that should come to your mind is that SE is equal to K plus B theta C divided by theta YK minus B. Okay. Sounds good.
Theta C on the bottom?
Theta C, right. So yeah, I have it here in my solutions that at the bottom it is theta C because I think I made the assumptions beforehand. Yeah, it's theta C originally. Okay. So you have theta C here. The question did say that your mean cell residence time is how much? 1 day. Okay. So your theta C is 1 day. And you have all those different parameters. Okay. And you just solve for SE. All right? Simple enough. And then the second thing is they ask you for the biomass concentration, right? Biomass is equal to X. Okay. Theta C, Y, and the difference of the substrate. And then here you have theta. Here you have theta. Is 1 plus theta C, theta C. Okay. And here's where this comes in play, right? There is no recycle. This is the case. Right? So this becomes then theta C. We cancel out this. Okay. Let's say the question did not say let's say the question did not say that there is no recycle, that there is recycle, right? And then now this does not cancel out, but you know that Q is equal to what? Is equal to B
divided by.
V divided.
Yeah, volume divided by time.
Right.
Oh, yeah.
Yeah, yeah. V divided by theta. Okay.
You're on the bottom of the X equation.
Yeah, sorry. This is theta. Okay, so if you have theta here and it does not cancel out, always know this relationship. Keep this in mind. All right, because then you somehow have the volume, somehow have the flow rate that goes into your system, can definitely find out what that number is. Even if it's not given directly in the question. Or vice versa. Many times in the homework, we would say like find volume, right? Or something like that. So this is how you find the volume. You would substitute this theta using this volume here. So if you want to find volume, this theta, we'll just change this theta. This becomes V divided by Q. This Q goes up here. So you can manipulate it so many ways by just knowing this relationship. So for now, it's just theta C, and it cancels out with the one at the top. And then you find whatever X is, your biomass. All right? So the next thing, the question is telling you to find this thing called a utilization, specific utilization, right? And food to microorganism ratio, FM, okay? So to solve for the specific utilization, you will need to first actually solve for the food to microorganism ratio. And I'll tell you why. Let's just get rid of this.
What is specific utilization?
So it's the specific utilization based on how much substrate your system uses and how much you added in, and your food to microorganism ratio intake. So I'll show you how that looks mathematically. There's the specific utilization of your system. Okay, so you have a food to microorganism ratio that tells you how much food you need to add depending on how many microorganisms you have, right? So in other words, how much substrate you need to add depending on how much microorganisms you have. Okay, a specific utilization is showing you, well, you're not using all of your substrate. You're using a little bit of it because you have SE coming out, right? You have a certain concentration of SE eventually coming out. So that specific utilization takes into account how much your system is actually using of that substrate. You'll see that mathematically. You had a question? Or,
And a substrate is an electron donor.
okay. So, we'll get to that in a minute. I think that's a great thing to refresh back to again. So substrate is an electron donor, yes, and we'll write it down again to see why that is the case. Okay, so
That's what we're cleaning out, right? Substrate.
Yeah.
And substrate with the food for the bacteria. Yeah.
food over microorganism is equal to your substrate, right? Your food, your substrate, over the x theta. Okay, the equation. I mean, so far, all the equations that you need to use to solve a particular question has always been given in the exam. So I would guess yes, it would be given.
That's S naught.
S naught, yes, whatever you started with. Okay. The reason we multiply by theta is it's a rate. We want to find out the rate. Okay. The rate of this food to microorganism consumption. That's why we divide by the hydraulic residence time or the mean residence time. Okay. So whatever you find a value here, and that value gives you the rate of the food consumption based on the microorganisms that you have. Does it make sense? Okay. So you have, let's call this value, you have F over M. What is specific utilization? Call it U. It is it's also Fm, right? Start with Fm. But because it's a specific utilization, this is where the difference come in. You have SO minus SE, okay, divided by SO. That's what makes it a specific utilization, because you're not consuming all of your substrate that you have. Okay, you have some substrate that is coming out, that is still coming out of the solution. So imagine if you consumed all of your substrate, what happens? No, not from that perspective, from a mathematical perspective. So if your SE happens to be fully consumed, your substrate is fully consumed. Look what happens here, right? This goes to 0. This S and this becomes equal to that. It's not specific anymore. You don't need to be specific because you're just consuming everything, right? But we want it to be specific when you don't consume all of your substrate. That is the reason we use this. Does it make
We
sense?
also go for the units.
Oh yeah, sure. So let's see here. Units of this one, I believe, is milligrams per liter. Substrate milligrams per liter. That's I wrote it down as milligram substrate rate per liter, and this is milligram cell per liter times B. Okay, so if it's strictly units without substrate or waste or cell or whatever, these two cancel out and it's just a rate basically, 1 over D. Okay, and this one is also 1 over D, because whatever units you have here, they all cancel out too. Okay, this here is simply a ratio. Okay, this is a ratio, and it's unitless, no units. It's the same. This has the same units as your F over N.
How are these related to data?
Is the F over M, I know in this example, theta and theta C are the same, but if they were not the same, would that be theta C?
Yeah.
Okay,
Because this is relating to the biomass.
okay, yeah.
Okay, so then they're inversely related to the C and F over N.
Theta C and yeah,
Okay.
yeah, it is. So the longer you have it in your system, or in other words, the more recycle you have, right? Because theta C goes up with recycle. The more recycle you have, the less F over F would over microorganism ratio that you have. What does it mean to have F over M to be low? Right? If this ratio is low, that means your food is not enough. Your food is very low. You have a lot of microorganisms, but you don't have enough food. So if you increase your mean cell residence time, this ratio goes down. It's just telling you, okay, you need to add some more food. Otherwise, we're starving here. Right? This is what it's telling you.
Thank you.
Yeah.
Yeah.
We go over the electron donors and acceptors and stuff.
Yeah. Can we do it for nitrifiers and nitrifiers? I have the equation.
Try. Okay.
Because you mentioned that like quite a few times in class, so I feel like it.
All right.
I thought- Yeah.
That's so good. The bottom of it.
What do you guys want?
It's a great question. And, you know, yeah, but this is- we learned that.
For what?
Oh, yeah, we're gonna grab all this. Remember how you said that? Like, there was a reason why implicit methods weren't as good as, you said, we'll come back to it. And then come back, guys, we're coming back to it today,
That is fun.
so.
You guys look at the other.
I worked in.
He says the next lecture to be.
Oh, I didn't
Yeah.
think about that.
And before.
Makers?
So we'll do the nitrifier, denitrifiers, but let's do one basic equation.
Okay.
Like with the substrate, oxygen, whatever, and then I will go from there. Okay. So can you just, I think that you had an example with methane, right?
Yeah.
Methane plus what, oxygen, was it?
Yeah.
That gives you CO2. And H2O. Okay, so from here, we'll just define the basics of the electron donors, why they're called electron donors and the electron acceptors and vice versa, right? So before we start, the first thing you need to keep in mind is that a reducing agent, okay, a reducing agent is an electron donor. Okay, and an oxidizing agent is an electron acceptor. Okay, so keep that in mind. So how do we define something if it's a reducing agent or an oxidizing agent? We look at the oxidation number. Okay, so here we have methane. Okay, so can you tell me what is the oxidation number of this carbon? Negative. Why is it -4? Okay, because hydrogen is known to have an oxidation number of +1. Okay, you have 4 hydrogens here, so that means this hydrogen is +4. Okay, which means this carbon needs to be -4. Why? Okay, I see some confusion. So hydrogen is always going to be +1. Okay, that's hydrogen's oxidation number. So I'm going to write this mathematically. So you have X is the oxidation number of carbon. I don't know it yet. And you have plus the hydrogen, okay, which is +1. Makes sense? You have 4 of them times 4. And there isn't any negative charge associated with methane. So that's equal to 0. Okay, so this X, if you're solving for X, which is the oxidation number of carbon, it becomes -4. We get there? So that's how we define the oxidation number of carbon. It's -4 here, and hydrogen is +4. Okay, so what happens to the carbon? On the other side, it goes to CO2. Yeah? Okay. I did this. I want you all to do this. Okay. How can you find the oxidation number of this carbon?
Find the oxidation number of oxygen.
Okay, what is the oxidation number of oxygen?
-2.
-2. What's the next step? What's the next step? Follow. How do you find the oxidation?
You multiply -2 by 2 to get the total oxidation number on oxygen.
Okay, sure. -2 multiplied by 2, and that gives us the oxidation number of oxygen. And then what?
Plus X should equals,
I'm sorry?
X plus -2 times 2 should equal 0.
Okay, yeah, X plus this should be equal to 0. Make sense, everyone?
Mhm.
Yeah. And then now this X becomes what? +4? So this carbon is +4. And this oxygen is -4. So notice what happens here. You have something that's going from negative, means it has more electrons, okay, to something that is positive, which means it has less electrons. What's this process called? Oxidation or reduction?
Oxidation.
Oxidation.
That's what I was gonna do. I didn't learn it, but you said.
Oil rig. Okay. Oil rig is an acronym to remember this what's happening here. So oxidation, this is what it means, is loss of electrons. Okay. And rig is reduction. A bit low. Rig is the reduction, is gain of electrons. Okay, so just a quick way to remember. I'm just going to get
How do you know the oxidation number of like hydrogen and oxygen?
So these are set. These are known oxidation
You have to
numbers.
memorize them?
Yeah, those things you need to memorize. The hydrogen and the oxygen are two of them that you need to memorize. Hydrogen is
any
plus.
others?
I'm sorry.
Are there any others that we need to know?
No. For the purposes of what you're doing, maybe chlorine is -1 is another one. Chlorine is -1. Fluoride is also -1. Oxygen is -2 because it's on the it's one step to the left of the periodic table.
So it's like the related to how many valence electrons it has?
Yes.
Okay. That's great.
All right. So if you're going from negative means more electrons, to something more positive, then you're doing an oxidation. And if this species is undergoing oxidation, is it a reducing agent or an oxidizing agent?
Reducing agents.
Correct.
Oh, it's so annoying.
I know, why do they do that? Who names these?
Yeah.
Reducing agent. Okay. So if it is undergoing oxidation, then it's a reducing agent. Okay. What does a reducing agent mean? Electron donor. So does that make your substrate electron donor or an electron acceptor?
Donor.
Yeah.
Also, a substrate can also be not.
No. Yeah, I don't think. I think the substrate is. I think the substrate is always going to be electron
Okay,
donor.
that's what I thought.
Okay. Yeah.
If there was like, if there was a nitrogen source
Mhm.
in this,
Yeah.
would it just not be a part of the redox reaction, so we just wouldn't consider it?
So if there was a nitrogen source here,
methanol.
For denitrogen.
No, but just like,
No, for.
It would be, like we said before, if there was like a biomass, like you say, you have CH5O2N.
Yeah,
There is no way that you know what this C is,
yeah,
so that you can solve for this N.
yeah.
You cannot do that,
Yeah.
okay? However, for some reason, let's say you have ammonia here. And then your reaction combusts to form N2,
Uh-huh.
right? This is something we can do,
Yeah.
right? Because
I don't know why.
what is the oxidation number of N2? Zero. Oxidation number of N2 is zero. Or oxidation number
So
of any
multiple-
element.
Wait, can multiple redox reactions be happening at the same time?
Yeah, if your reaction is reversible, it will definitely happen.
Well, I'm like, so you can have a
You can-
redox reaction of the ammonia to N2 and a redox reaction of the.
So what does redox mean? Redox is a combination of oxidation and reduction happening at the same time.
Yeah,
Okay, so you have oxidation here happening. If we just take a look at what's happening to this oxygen, what is the oxidation number of oxygen is zero, right? What's the oxidation number of this carbon? I'm sorry, of this oxygen here. So what's happening to the oxygen? Is it reduction or oxidation? Reduction, right? So you have reduction happening here, and you have oxidation happening here. It's already a redox reaction.
but then if you add the ammonia to N2, that could also happen.
Well, the O was -2.
So when it's in its element, in its gaseous element, then it's zero. So if it is within a species itself, like for example, carbon or water, then it will become -2.
Okay.
But if it is, if anything is in its element, like for example, O2 gas, N2 gas, these have oxidation numbers of zero.
Okay.
Okay, so keep that in mind. It's important. Okay. Good. So if we have ammonia here for some reason, can we figure out the this is actually a great segue to your denitrifiers or nitrification, for example. So can you give me one of the nitrification processes that are happening? Or the denitrifications, so the species that are being involved. That's enough.
Yeah, you want to cover.
Okay. We can get to that in a minute later. I think it's a bit different. So anyway, so if there is an ammonia here, so can we calculate what is the oxidation number of this ammonia, of this nitrogen? -3, right? Makes sense? Okay, so this is -3. This is zero. What's happening to it? Which means?
Which means it's the electron down.
It means it's a substrate. Wait, does that mean?
Well,
it's a-
no. So it's simply an electron donor.
Yes.
Whether it's a substrate, perhaps it could be. Biomass, maybe it's using it up as a substrate.
But just if it's a substrate.
Well, it really depends on the biomass. Actually, it might indeed be a substrate because your cells require ammonia to survive, right? So it's being taken up by your biomass. Yeah.
So sometimes it's called like a nitrogen donor versus a substrate.
Nitrogen donor.
Or like
Versus a
carbon don't, like sometimes he says.
Yeah.
stuff like that.
Sometimes they say assume ammonia as your nitrogen source is
Yeah,
what they say, right? So yeah, it is the nitrogen source. So if it's a source for something, then it means it's a substrate.
Okay, So, okay, those are listed
Yeah.
the same.
So if this is good, we can go over some examples of denitrifications and nitrifications here and see what's happening to them.
Can we do like, when we go over it, can we like kind of go over like what the carbon source is for each one and then what the electron?
Yeah,
Okay.
yeah, so yeah, we can do that. I can do that for the nitrogen. The carbon source, however, it's hard to identify see, I'll write down one of them and that will be self-explanatory.
Okay.
Everyone's good with that? I think it's still recording. Hopefully everyone can see. Yeah. Okay. Erase this. All right.
Here's 13.9.
Okay. So. I'm going to write this equation down here, which is the nitrification.
We didn't really talk. I mean, that's fire, really.
Not really.
It's just kinda like.
Yeah, that's what you can.
Yeah, I think mainly we were just.
Doesn't matter though, when you're trying to identify what is an oxidizing agent or what is a reducing agent. The moles in front of it though, it doesn't. Okay. Okay, so.
And then this takes care of the.
The BOD. This is where he does like the mainstream. This is
So,
like this goes anaerobic.
This is our equation here, okay? So this equation is a
Then
nitrification
was like, you know,
equation because what's happening here and what's happening here is causing this nitrification process, all right? So based on those two species, we want to identify if this is an electron acceptor or electron donor, right? So let's do it together as we have learned, right? Let's start with ammonium. Okay. What is the oxidation number here?
-3.
Negative, oh, because of the, yes. You have tricked me. Let's do it. Let's do it mathematically, okay? So you have 4, right? Because of the hydrogen. You have +1. Okay, each hydrogen is +1, and that's equal to
+1.
+1. It's not 0 anymore because there's a charge to this ammonium, right? So if you're solving for x, it becomes -3. Okay, so the oxidation number of nitrogen here is -3. Okay, what about this nitrate? Okay, sorry, I don't think you're able to see it. So this nitrate here, okay, what about this one? Can we do it together?
Mhm.
Okay, so we have x plus 3 times -2, right? Because we have 3 oxygen here, -2 for the oxygen, and that's equal to?
-1.
Cool. So you have -1 plus 6, which is equal to? +5. So this nitrogen is +5. what's happening?
Being oxidized.
Being oxidized, becoming more positive, okay?
Oh,
Oxidation, which means it's a, which means it's a, okay? We cannot do, we don't know about like the carbon, you might ask about like the carbon source here. It's difficult to do this carbon, carbon source using this method because of the biomass equation here is C5 H7O2N. Okay, we know that oxygen is -2, hydrogen is +1, but there's no way to know what this carbon is.
Right, because of N.
Because of N, yes. Because there's there's N and C. Those don't have fixed oxidation numbers. It depends on the species around it.
Yeah, but like carbon dioxide in this case would be the carbon source
Yeah,
of rock. Okay.
yeah. Right. It'll be carbon source overall. Perhaps there is a way to do it based on the oxygen that is present on this carbon and the oxygen present over there in the water. And that might give you an idea of the oxidation number.
Oh,
So the oxygen here is -4, right?
mhm.
And the oxygen there is how much? -2, right? So what's happening to it? It's oxidizing or reducing.
Oxidizing.
It's becoming less negative, more positive, which means it's an electron donor as well. Which means it's acting as a substrate. We good?
Yeah.
What about denitrifiers? Can I have that, please? Can you pass that, please, India? Thank you.
So, do denitrifiers use methanol as a food source?
Yeah, it does say here that it's using methanol as a carbon source.
As a carbon source.
Yeah, and we already know why is it using it as a food source. It's an electron donor. Right.
So that's a substrate.
That's a substrate. But what about this nitrate? Is it acting as a substrate or is it acting as a electron acceptor, right? So instead of writing this entire equation, I'm just going to actually write the nitrogen sources. I'm just going to raise it. You all good with this? Okay, so I'm just going to write down the so we have nitrate, and that's going to nitrogen.
so you do.
Okay, what's going on here? We have nitrate. Again, to solve it, X plus 3, right? 3 oxygens, -2 because they're oxygens, and that's equal to -1. Good. So that's X becomes, if you're solving this, +5. So this is +5. And what about this?
0.
What's happening here? Yeah. A bit of change of flavor, right? So this here is reducing because it's becoming more negative or less positive. Okay, so this is reducing. Does that make it an oxidizing or reducing agent?
Oxidizing.
Agent, which means electron
Acceptor.
Oh. Does that make sense?
So is denitrification just turning it into N2? Like what?
Yeah, so denitrification is turning this nitrate into N2.
Okay.
So what you're starting with is you have some sort of ammonia or ammonium. That changes to like ammonia in the solution somehow, and then that goes into nitrate. Actually, it goes into nitrite first, and then goes to nitrate. Goes into nitrite. What was the formula of nitrite? Was it -2?
I think it's just.
No, negative, yeah. And then it goes into nitrate, and then goes to nitric gas. There's the whole process. So you're denitrifying and then nitrifying. Okay, this here, this is unstable. Unstable. So in the same sheet of this denitrification and nitrification, you're asked to find out like what is the methanol dosage, right? One of your homework questions. Remember, what is the methanol dosage? And in this question, they told you to use this formula. Plus 1.53 NO2, okay, and plus 0.87 PO. Okay, so you're able to calculate this from your substrate equation, your substrate effluent, but this one, what did you do? You approximated at 0. Why? Because of this state. Okay. And this is your dissolved oxygen. Okay. So keep that in mind. This assumption is most of the time usually made.
And then did the coefficients for that equation just come from like stoichiometry?
That one? Actually, I'm not sure. I'm not sure, but my guess would be yes. Yeah. Okay. We all good here? Yeah. Any more questions?
And we like to just talk a little bit quick about like how, I think this was on like homework, how like you convert from, or like when to convert between like VSS and like TSS, because I know we've seen like MLVSS
Yes. Okay.
versus like MLSS.
So to answer, okay, that's a great question. Thank you. So to answer that question, we need to know why things are reported in VSS and why things are reported in TSS. Okay. So why are things reported in VSS? What does VSS mean? Volatile suspended solid. Okay. So, and then you have TSS, which is okay. So whenever you are talking about biosolids or biomass, it always has to be in VSS. VSS is everything that is combustible, okay, that can catch fire and combust. And that means everything that is a biomass. There are certain things that cannot combust, and those that cannot combust are not biomass or not biosolids. Okay, so it's important when you're denoting a value of mass of a biomass, you need to write it down in milligrams VSS you need to write it down in like units of milligrams VSS per liter. That means it is a biomass or a biosolid. Okay. A TSS, on the other hand, a TSS is everything. It's like if I give you 10 grams of dirt, right? And in that dirt, there is like some plants, right? Some branches, some soil, some whatever carbon source is there, like some worms for some reason, and then you combust that thing, right? You're going to be left with a volatile mass that is not going to be 10 grams, which is what I started with. Maybe it is going to be like what we have as an empirical approximation is 80%. You see, there's 80% of biomass within a given amount of solids that we have. The remaining 20% are not combustible. They're not biomass. They're something else. Okay. So that's what it means. So if I'm talking about biomass, like if I tell you how much biosolids you have in that, handful of dirt, you will have to report the value to me in, oh, there is 7 milligrams VSS per liter. You cannot tell me it's 10. That's not biomass. That's total solids. Okay. So that's what this means. Sorry, was there a specific question? Question 10, right?
Not like,
Oh, you mean like the conversion, right?
Yeah.
So the conversion, also keep that in mind. I'm sure it will be given to you in the exam, is that it's 0.8 VSS over TSS. Okay, which means there is 80% VSS within a given amount of TSS.
so if we're given like MLSS and we
Yeah.
need like
Yeah.
substrate,
Okay.
how would we convert it?
Yeah. Okay. Let's actually walk through that problem. It's homework 10, right?
I think so.
Okay. So I will walk through some of the things that are given that you had to do some unit conversions in. I'm going to erase this. All right. So part C is an example that part C in that homework 10 told you to find the total effluent BOD. Okay. But in that question, you did a unit conversion, not because you wanted to report an answer in VSS or TSS. It's because you just wanted to make sure everything is in the right order of units. Okay, so this equation here, you have your SE, right? Your substrate. You have this. We have these in your notes as well. You have your SE, and then you have your XE. All right. And it's being multiplied by 1.42. Okay. And it's being divided by the ratio of BOD 5 over BOD of it. And then we've done a conversion of the 0.8 VSS over TSS. So the reason we do this conversion is because right. So the reason we do this conversion is, by the way, this value here, because it's a BOD, it's a biological oxygen demand. It has to be also reported in VSS, by the way. Okay. So this is in milligrams VSS per liter. Okay. The question gave you that XE is 20 milligrams TSS per liter. So This was in VSS. All right, because it's BOD per liter. And this was in VSS, so you need to convert it to VSS using this conversion rate. Okay, and then the final answer will be whatever, like whatever that is. Milligrams VSS BOD5 per liter, or BOD per liter.
What's the difference between FE and XE in this equation?
So SE is the substrate. Is the substrate outlet, your BOD substrate outlet.
So what's the XE then?
XE is your biomass. XE,
Would it be TSS and for the biomass? Isn't it all
yeah,
biomass?
it's not the correct, it is not the correct representation, but you could write it in TSS if you want to, that's fine.
Okay.
Like, let's say I had an XE reported in, I don't know, 8 milligrams VSS per liter. If I have a coworker that does not like me, he will report it in TSS, right? He'll just change the units using that conversion rate, which is that 0.8. But now if you want to convert from VSS to TSS, you'll have to divide by 0.8. Keep that in mind, right? Because the conversion is 0.8 VSS over TSS. Okay, so if I want to convert VSS to TSS, it'll have to be 1 over 0.8 TSS over VSS. Does that make sense?
Yeah.
Right? So that's how you can report it however you like.
I was confused by the XE being TSS.
Yeah,
Yeah,
yeah.
that makes sense. Okay.
So is like mixed liquor suspended solids, is that the same as like concentration of total suspended solids, like, or is that the same?
Yeah.
Like,
You
they could be given either way.
mix
MLSS.
MLSS, yeah. Mixed liquor suspended solids.
But then a few problems we were given that. and
Yeah.
Had to like,
Yeah, no, that would be in VSS, I believe, yes. Let's see. Okay, does that make sense, everyone? X and C. No. Yes, mixed liquor suspended solids is VSS.
VSS.
Yes. Because in that question, it's given to you as 3,500 milligrams, right? Yes.
Okay.
Yeah.
Mixed versus. Yeah, and I think also question or homework 11 used, and it's MLS, yes. Yeah, so if you go back to homework 11, question 2, part B says you have your mixed liquor solid concentration and it's reported in milligrams VSS per liter.
Okay.
So you can use the units to tell.
Okay. Ideally, the units should always be reported, whether it's TSS or VSS. You do the conversions appropriately.
For problem 4,
Of which
for the
homework?
practice exam, the X's are still the biomass, right? Or would that be substrate? That's the biomass still, right?
Problem 4, let me see, I'll take out the exam here. You
I
have
have it right
everything?
here, so it just won't work.
Yes.
It's all just like X's. So like
Yeah, so that's biomass.
Biomass,
Yeah.
okay, yeah. And then for finding the VL, I understand that it's gonna be like the lowest part of for the local minimum of the GT. Since there's no equations to this, you're kind of just estimating.
Yeah, so GT, the estimation of that, the GL, you mean, right?
Yeah.
The GL,
So it's where like the local minimum would be like this is the GL, if like the GT's local minimum was right there.
So
That's where you just add.
So the local minimum
Yeah.
would be, okay, so here, I will write it here, okay?
Okay.
So, there's a question about exam, practice problem, right? You have your graph here, that's question 4. So your y-axis is,
Yeah, I guess we like
flux,
everything.
solid flux,
And then, oh yeah, it's BT is GS plus.
okay?
G,
And this is
Okay,
sludge
so
concentration.
yeah, and then BB is BB.
Right? Your graph initially looked like this. But after you do your GT, your total flux, right? To find GL, it looks something like this.
With the conversion to get
Because GB is always increasing.
like second point.
Does it curve up in the end? Like,
Or like
does
the
this curve up?
Yeah, the GT.
And then add them together.
No, so it will, okay, so let's explain how we got this curve and how we got this curve in the first place, right?
I like don't know how it is.
Mhm.
So you wanna know what your, so this curve here, let's do some definitions, okay? This curve here, we'll call GG.
There might be
Okay.
a point where actually.
We wanna get
add them together.
G total,
Spot it and be like, oh, no.
which is equal to GG, which is this curve, plus something known as GU, your outlet flux, which is here. This is GU, okay? And this here is like 10,000, right? This concentration here is 10,000.
Yeah.
Okay.
Yeah.
So we want to, someone talking? Okay, so you want to find what this total graph, what this total GT will look like, because that's where you get your GL from. We'll get to that in a second, right? So this will be a straight line, okay? So to draw a straight line, you need 2 points. Okay, we know 1 point is here, 0, 0. Okay, that's 1 point. Okay, we have another point here at the very end. This is the sludge. You remember like the clarifier? That is like the things that come out of the clarifier, the secondary clarifier. This point here, this is like this point at the very end of that clarifier.
Yeah.
Okay, this is where this point here
Yeah.
is your GL. Like this point here, if you this here is GL, okay, the minimum, but not this one, but I'll show you. But in general, the minimum of the graph is that last point. Okay, but I'll show you what GL is in a second. This is okay. So this we're going to define this as GU. So this is GU. This right there. Okay, so
I feel like we went over this, like.
no, not
again.
not GU.
Yeah.
This is GG for this graph, the minimum of this graph here.
Is that just gonna be the GS?
I'm sorry?
Is that just the same thing as GS?
Yeah.
Yes,
I
yes.
only remember GS and.
Yeah, yeah, okay, GS and GB, so this is GS. Okay. We'll stay consistent with that. This is GS. All right, and all right, so this is GS. This graph also is GS. This is GS, okay, and now you need to find GU. Okay, it's another curve because G total is where you'll get that GL from. Okay, that minimum from the GL.
Yeah.
But we need to find what GU is. We have 1 point here. We need another point to connect it to this. Remember, what is the equation of flux? It is the velocity times the concentration. Okay?
Okay.
That is the equation of flux. So if you want to find flux, if you want to find flux and you're given velocity
That's literally
and
the
concentration,
velocity.
which is what you did in homework 11,
Times
Yeah.
concentration.
right?
So you go
So-
to
It's just the VB times the concentration, right?
Right, exactly, VB, so
Yeah.
That's always gonna be increasing linearly.
precisely,
So then what if, so what if the curve at the end go up?
no. So it will stop, so it will stop where this stops.
Okay.
You see what I mean?
Yeah.
So, okay,
So we have to come.
let's say after you do this calculation, you'll get a value of 0.4. Okay? So
The
when you go home, try to do the calculation yourself, you'll find that when V is 0.4. All right?
minimum line.
So when
is
it's
the
0.4,
GT.
that's the next point,
So
okay?
like,
So this value here,
I feel like that's.
this value here,
So here's our GT.
this
which
point
we
is
could-
0.04.
Here's the minimum. And then-
This from the graph.
When you're multiplying
Okay.
the VB times that 10,000.
No. So just by looking at the graph itself,
If I'm.
just by looking at the graph itself,
Median.
this point here at the very end, okay, is
Yeah.
0.04.
Yeah.
That's my GS.
So you get like.
Okay, and now to find GB, you'll need the second point, which is 10,000, which is the lowest point that's coming out of your secondary clarifier. And it's going to be, let's call this point 0.4.
Yeah, that's like GS.
Okay, so the second dot here
And then we like.
is going to be here.
Or if you would just give us.
That's the straight line. You talked about a straight line, right? So this is the straight line.
Or you.
That's just a go to
That's GB.
Okay,
Okay, that straight line curve, we call it GB.
which is equal to VBC, right?
Yeah.
Okay.
Yeah, the equal to VBC, this is how you find it, right? But we only needed 2 points. One of them is here. To find the other point, the VB times C, that's this point here. But yeah, the entire curve is equal to VBC. You're doing VB times C, but like that C concentration will vary as you're going across the curve.
Yeah.
But we wanna know the end point only. So we wanna know the beginning and we wanna know the end. We draw the curve,
Okay.
okay? How do we get GT? So GT is the addition of those two curves. And you said it keeps going linear. Yeah, but it can keep going linear. That's true. I'll see you later. It can keep going linearly, but GT, that curve will stop here, because that's where the sludge ends. This is the maximum sludge concentration.
Okay.
So when you add those two curves together, because this is a linear curve, all that is gonna happen is that this curve is gonna shift upwards. It's gonna look like this.
Okay.
Makes sense? So if you're adding a curve,
Still though, at the end,
Oh,
like,
yeah.
from, if you're adding
Oh, wait.
this to this,
Mhm.
this to this is
Oh,
gonna be a
they-
bigger number, so why not
So
go up?
it's divided.
Both.
Because in class, he was telling us that the
yeah.
minimum of this line is gonna be where the GL is.
you're right. Actually, so the curve, the curve itself, will probably look like something like this. Okay, so it's the addition of this plus this to give you that.
Okay,
Yeah, you're right. But it will not shoot up like that.
yeah,
Okay, that will not happen. But yes, it's above the line.
okay.
Okay.
And
So-
where are you getting the point for from again?
So the point 4 is from just looking at the graph itself. So from question 4, if you open up your question. So you mean this one, right? You mean this one or that one?
I guess,
Both?
well, the 0.04, I understand you just.
Yeah, okay, so the point 4 is from doing this flux equation. The flux is equal to the velocity times the concentration. The velocity is given to you in the question.
Yeah,
And VB, which is what number? What number is it?
4.79.
4.79. If I multiply that by 10,000, okay, do a unit conversion. You need to do a unit conversion. There's a 8.34 is a unit conversion that changes. Okay, so 8.04, you'll notice that as a common unit conversion. So it's something that takes
Yeah.
something that is being multiplied as milligrams per liter with like million gallons per day.
Yeah.
If you multiply it by 8.34, the units that come out of it is gonna be pounds per feet cubed per hour.
But then he's still adding
Okay?
to it,
Alright.
right?
Keep going. So, right. So when you do this calculation, you'll get this. You'll get this number here. Okay? Okay.
Oh,
Negative
Um,
VQ per hour.
yes.
Okay.
So then.
So this will be this point here,
GV is just.
because we need 2 points to draw the straight line. So this is our straight line. And then once we have our straight line, we can get our G total by adding that and that together. Okay. And guess what this number is? Yeah. The GL. Can you tell me what number that's gonna be? 0.04 plus 0.4. Exactly. Yes, yes, precisely. So that is your GL. Okay. That is your GL.
So
Okay, so here's another thing. This is very interesting because your GL, this G now, your graph shifted upwards. That XU value, okay, so this value here that comes out of the reactor, remember when we do this reactor, we call it XU, right? In your question, I believe it calls it something. Yeah, let's just keep it as XU, okay, because that's what we're used to. So this is XU, okay, so this is XU, this is XU value. But because this shifts upwards, that XU value is going to also shift. So how do you know where it's going to shift to? So you have this straight line here, you're going to extend it further. You're going to extend it further. You're gonna take that GL value that you computed, go over until it intersects and come back down. And that is your new, that's going to be your new XU. That takes into account, that is from the G total. Curve.
So for GS, like did you just get that by like looking at the, like where it intersects with
The GS, you mean this?
Yeah,
Yeah, so that is this point here, the lowest point. What that GS is, yeah.
Mm.
So this part here is a bit confusing because you have not done something like this before. And when you did it in your homework, you just approximated that the XU remains the same and you did not change the XU. Okay, but here when you're given graphical data, you can calculate your new XU. And you'll notice the difference is actually not that much. It's just like 1,000. Or something.
So when,
See you later.
on the handout here, like when we're given this, would
Yeah.
this be GT?
So,
curve?
right.
Or you would approximate?
So in the handout, just, okay, so in the handout, things are, it's slightly different. Okay, so in the handout, you were asked to compute the what you call the GL based on your tangential line. Okay, that's another way of doing it, is that you start from here, okay, your lowest point, and you take your line and you draw it that way. Is another method to getting GL.
That's if you're given C in the problem.
Yeah.
And if you're given VP, then you use the other.
Right. So if you're given VB and if you're given like some graphical data like that to plot things on it. But in general, G is equal to C times V. Okay. And if you're given graphical data like this, okay, if you're given graphical data like this, regardless, like you're not given VB, okay, you're only given CU, you're going to take that point, that sludge outlet concentration, take that point, find the tangential line, okay, bam, find the tangential line, extend that line all the way to your y-axis, that value is your GL. Make sense?
So this,
So this method of taking the curve and then adding it to the other curve and then doing this stuff, it's very specific to this question. Meaning it's unique to this question. Okay. In general, to find GL, you do it this way. The tangential line.
Just from
that curve.
Okay.
Just from that curve, take the tangential line and find it.
so is the curve that you like use for that, is that what we're talking about right now is like VS or is it VT?
This curve?
Yeah, like where you,
VS.
okay, so even in this example, it's VS.
Yeah.
Yeah.
I believe so.
Okay, thank you.
Yeah.
All right. I don't know.
Come back and rot here.
No, I think I'm gonna sit in, sit in.
Yeah.
Yeah, that makes.
Kind of flip this in line.
Well, okay, I already did know. I am super hungry. I do wanna go get a coffee. So maybe a little quaff. Let's say I do a little quaff and then rot here, not in Cityville. I don't want to. Rot somewhere
I'll
else.
pay for your stuff.
Why is there two? Why do you
I
have two
messed it up. I
Okay.
messed it up.
Yeah.
Okay,
It's
so
not-
it's-
it has to be- it's on the side.
Okay, so yes, it has to start from here because this is your CU value.
Yeah,
Okay. Because then we have to do it.
That's from,
Okay.
So that's right. This is how you're supposed to do it.
okay.
what's process of right now?
All right.
Thank you.
And
Thank you.
what else should I talk to you
Oh,
about?
that's that far. Let's. check.
It's not that far.
Bruh,
Well, it's far from my, yeah, it's not that far.
Oh, do you all have a minute? I wanted to talk about something you might have forgot. Two things. One is the linear Weaver plot,
Oh,
okay, and the other is the grid chamber calculation.
yay.
Oh, we don't.
The grid chambers stop a lot. But can you go on the one where you're-
The linear Weaver, yeah, we'll do that. We'll start with that, and then we'll go on to the.
Also, after that, can you
Hmm.
just briefly mention like what was going on with problem 3 on the practice?
Problem 3.
Oh, yeah.
The RBC.
Oh my God, yeah, that is,
Also.
that is very confusing, because not only do you have to, first of all, you need to find the area based on this very weird calculation of multiplying RBC. You have 4 different RBCs, you have, the blade itself has a
Yeah.
the diameter that you need to find, and then, but half of it is submerged, so you multiply by a half, but then you have 2 sides to
So
them.
then it's 1.
So it's 1, so that's your total area, right? So it's very strange. And then you'll have to do a guess. And after a guess, you'll have to double check again with your G value, yeah. So I think, can I see that question, please? Yeah. So I think what this problem is trying to tell you is it's trying to help you practice the relationship between the J value, right, the flux, and the substrate concentration, and how you can like move between them. So let me just take out the solutions as well real quick. And then we'll go. Are you in a hurry? This is fun. All right, so
I can't believe that's
take a
like,
resume again. Right,
That's
so
graduate.
That's actually, that's a lot. That was ridiculous.
Yeah.
no, I hope you're all gonna graduate. Don't worry.
I don't know, but it's very like, you guys.
Has this been your hardest class yet?
Yeah.
Absolutely. Yeah.
Well, that was.
Well, maybe not the hardest, like the entire time I was here. It's It's just like not relevant to, I know physics, I know
I see.
structural,
Right.
like I don't know anything.
This
about
is,
that.
yeah, very, very irrelevant. to
Yes.
your- I see. Well, we're almost over, and I hope this final stretch, comes to your benefit. So to solve problem 3, okay, to solve problem 3, this thing is very important to notice, is that you have your in minus out, you have your reaction, okay, and then you have it minus the reaction, and that is equal to the accumulation value. Okay, so your in is going to be your Q naught
like,
S
Oh,
naught,
the washout.
right? Your out is
yeah,
gonna
that
be your
was
Q E
Yeah, it's this.
S
It's
E.
finding.
Well,
mm,
so the Q's are equal because we're assuming steady state.
It's a way that you.
Okay. Because you're
it's
assuming
only
steady
found
state,
here,
this
like,
becomes
yeah.
equal. So it's Q naught S E.
Okay.
Okay,
That's-
and then minus the reaction, which is J times A. Flux times area is your reaction. That's equal to 0. Okay. You know Q, you know S naught,
Mhm.
you don't know this, and you don't know this. But you have, the area based on that very convoluted area calculation. Right? So what the question is suggesting you to do, we'll just simplify this a little bit. Actually, no. So what the question is suggesting you to do is, okay, solve for SE. Solve for SE and
That's not minus.
right. So yes, so that's going to be Q naught S naught minus J A over Q O. And I'm going to simplify to S naught J A Q O. There we go. Okay, that's equal to FE. So what it's telling you to do, well, I am going to guess J. Okay, I'm gonna say, well, J is 5, right? I'm gonna guess J is 5. That's gonna help me solve the question. Okay, let's say I get an answer SE1. Okay, I go back to my graph. I see that SE from the graph is like SE1, but plus 1. All right, or sorry, like maybe something ridiculous, plus 100. It's completely off, right? Okay, and then I go back. Okay, I go back here again, and I guess a different value. So it's a manual iteration. Yeah, I guess a different value, so maybe 2. I solve it again. Okay, I go back to this graph from the exam, and then I see that I solved this is SE2 now, and from the graph, it shows that SE is equal to SE2 plus 0.5. Oh no, that's very close, right? So that's probably the answer. It's a close number. It's a good guess, and hence I have solved for J and I have solved for SE.
And the A is like total area of
Yeah,
biofilm. So
that's
like
correct.
from the nucleus.
That's correct, that's
Okay.
correct.
So
So
as J goes up, SE goes down,
as J goes up, what goes down?
SE,
No.
because you're just talking about bigger number then.
Well, we can actually see that from the graph itself. Does your graph increase as
Oh,
SE
wait, no.
increases?
Well, that doesn't really make sense though.
Why?
Based off that equation. If the J is getting bigger, wouldn't the C be getting smaller?
Then.
Where does J at? So then-
If J is getting bigger,
in,
then SE
Like
is gonna
area.
get smaller. Right,
it's like area something.
so what do you have in your graph?
The opposite.
Where does it?
So
J
your
is the
J is
rate
going
of-
up,
J
and
is the
hence your
rate
S
of how much it
is
degrades
going-
per area. If you multiply it by the area.
your J is going.
Like,
Third, is
Yeah.
that like why we have the two relations, like if we were to graph where there's an S slope intercept form, they would have an intersection point, that's kind of what we're iterating towards.
Right, right.
So it doesn't necessarily that they should have.
They should go up, right, I see your point. So it does not mean that if this is 20, this has to be lower, because that relationship might not even be correct. That number might not even be correct to start with.
Okay.
You know what I mean? That's why we do the iteration, I believe.
So if we didn't, say we didn't wanna guess, could we write it and like sketch out a line on the paper and see like, yeah, this is where they intersect? Would that work, or would that?
You will need 2 points to do that.
Well, yeah, I guess. Well, you would have the slope if you, because you know,
So
we
you,
know Q0, S0.
so this is your slope, you mean? QA over A over QO is probably is going to be your slope.
Yeah,
This is going to be your y-intercept.
Yep.
Right, so if this is your y-intercept.
well, actually, we'd have to flip it. 'cause the
Right,
graph has
yeah,
J on the other axis.
Yeah, you're right. So this cannot be y, because your y-axis is J.
But I think we can still do it though.
Your y-axis is J. That makes it a little complicated, right?
It's kind of nice to see.
You could do J, A over Q0.
I think they have so much shit. It's like that.
I know, same.
I have like so much
S
stuff.
E is
Like
your
homework.
X,
Yeah.
To do.
and J is your Y.
Not same.
I suppose you can flip
That
the
might not
curve.
even be- yeah.
Yeah, no, I think the easiest, I think what this question is trying to get to is encouraging you to think about this. Yeah. Encouraging you to know that when you have a reaction through, like through this reactor, this is how you can write it down. You know, something that's coming out, something that's coming in, and your reaction can be written down as flux times area. So I think this is the key point or the key message here. Because I can give you, I might not give you information to solve for like SE, like, you know, remember like the constants like Q, K, YK and things like that. Maybe I don't give you all that stuff. Maybe I just give you flux and I give you area. Area may be something you're gonna calculate, I don't know. But with that limited information, you need to know how am I gonna solve the problem, right? And this is another way to do it, by knowing this relationship. Okay.
So wait, you guess an SE. And
No, you
calculate-
guess a
Or
J.
guess a
You can
J.
either guess a J or you can guess an SE. It either works, and you just double check it with the graph.
Okay.
Right. Is that good?
I have a question.
Yeah.
In this specific problem, it says it's like 2 stages.
Yeah.
So do you just do this twice and then use the SE you solved from the first time as an S naught? for the second.
No, they gave you the SE from the
Oh,
first one.
they
to
do?
use as the S file for the second.
Oh.
Can we just do the board solution?
So then, yeah, you don't have to do it the first time, just.
Right, I
Okay.
believe so, and that's why we only use the calculation of, like, of 4, yeah.
Okay.
That's, we use 4 instead of 2 for the
Okay.
area.
So if we're doing a mass balance, anytime there's a flux, that will be a reaction component, not an.
Yes, it could be used as a reaction component, yeah.
And the area is gonna be the 500 flat discs. Times 4 IBCs, right?
Yeah, that's correct.
Okay.
Yeah. So remember, you got your SE equation, remember that equation with K and YK and all that stuff? By using a reaction of the Monod kinetics,
Mhm.
right? So that's how you got SE in the first place. But let's say you don't have the parameters of Monod kinetics, but you have experimental data. This is experimental data, your flux. This is something you calculate experimental, right? I can still find out SE. It's actually more accurate than doing it with the Monod kinetics. Monod kinetics is a model, right? But let's say you want to actually find the actual values. This is the experimental data. Okay. Keep moving, keep going. Two things I just want to make sure you all know about, and then you can leave. Okay, let's see here. Number 1 is gonna be I'm gonna go here.
Word class too.
No, I like that one. Yeah, I like that one.
Okay.
Not talking to worry.
Yeah.
Just like, pass everybody.
I just.
I sure can.
Okay. So
But at this point going forward, you can, like, it, right, if you failed someone, it would be bad. It's bad on
You
him.
can't fail us all.
No.
think about success. Don't think about failure. You can do this. Okay, so the first thing is, I just wanted to clarify that, again, if you have something written in milligrams per liter and multiplied by million gallons per day, okay? If you multiply by that 8.34 value, that 8.34 value has units of pounds, million gallons per day, right? MGD, times m milligrams per liter. Okay, this is gonna give you units of pounds per day.
Is the,
Wait,
I don't think the D is in the MG.
No, pounds
Oh.
per day.
yeah.
No, square foot is because we were dealing with
I think
uh
this is just in the gallons.
we were dealing with velocity back then. We were dealing with velocity at that other one. So it's not square foot, no. So the other one was, you have your concentration. And you had your, what was it, the value, whatever, what was the units of that velocity?
Gallons per square foot hour. Okay, so that's what it's like about that.
Exactly.
That makes sense.
Exactly. But remember, this is gallons. This has to be in million gallons. Okay, so there was actually it's not clear from the solutions, but there was another conversion there to convert this to million. And then you can use that 8.34.
Okay, and you have to convert the hours to days. I'm just- They're really round days.
Yeah, I think so. I think there's another conversion here that changes it from hours to days. So this, yeah, you're right. So there's one that goes from hours to days. And then you have another conversion here that goes from gallons to million gallons. And then you can use this. Okay. But in general, keep this in mind. All right? Okay. One thing is done. The other thing. We'll just practice. I'll show you the grid chamber again. What are some of the important things you need to go over when you're solving a grid chamber problem? Right? So, grid chamber. The first thing you need to do for a grid chamber calculation is that you need to understand that, first of all, you need to, usually what a grid chamber will ask you to do is find the dimensions of the depth, the width, and the length. Okay? Two things that are important is to find this thing called VH, the velocity that your grid chamber is going to run at. VH, it has to be between your V score, okay, and your V grid. Okay, sounds good. So to find, so there are, I'm sorry, yeah, they're both score, but one is grid and one is organic. Okay. Score. So this is like, has to be between the grid and it has to be between the organic. Okay, sounds good. So that VH has to be between those two values. It's important. Be between those two values. Okay.
So it has to be greater than grit because you want the grit to settle. It has to be less than organic because you're removing organic.
Right, exactly. Has to be between those two velocity parameters. Okay. And I can double.
If you want the organic, because
I thought it was the other.
I can double check that. Hang on. So instead of
It doesn't
Oh, yeah.
scour the, keep it symmetric.
Oh, the.
You want the organic.
You want the
Yeah.
organic to settle.
No, you don't.
You don't make it
You don't
settle.
want the organic to settle in the grid chamber.
Has to go, so it can go to the
Yeah.
aerobic digester. Or aerobic digester, sorry, whatever, the digester,
Um,
activity sludge.
Like the red chamber, the primary,
It's preliminary.
preliminary, it's just the primary.
Total solids.
Is that?
It's solid, like
something-
solids.
Is that the activated sludge?
It's not, this is
No, the
preliminary
primary
screen.
is like screen.
And then it's,
And then
No,
sec-
that's.
And grid.
that's preliminary. And then
Where's the-
primary,
Where's the
there's a primary clarifier that removes solids.
Oh, right.
And then the secondary clarifier and the
It's
activated sludge and it removes BOD.
Then what's the tertiary?
Nutrients.
Nutrient removal.
So nitrogen. phosphorus.
very good.
Brain.
Secondary remove solids, like settling solids. or-
Primary removes
Primary.
solids.
And then secondary.
Okay, so it is in fact, it is V score organic.
Yeah.
And it has to be between that and the V score grid. Okay. So that's the VH here, all right? So the next thing is that you need to know there are two areas. There is an A cross area, a cross-sectional area, which is the diameter times the width. And there's an A plane area, which is the width times the length. Okay. And so to find the V cross area, so keep that in mind. This is important. Okay. Two areas for grid chamber design: V cross and A plane and A cross. All right. So the A cross is the cross-sectional area. It's the diameter times the width. So if you go back to the solutions of this homework, there's a, so sorry, the depth times, what did I say? Yeah, depth times the width, okay? If you go back to the solutions, there's a diagram to show you what that means. Yeah, and I can also do it here real quick. So if you have and then this is your where do I have it here on my solutions? Right, so you have your depth is this is depth.
Oh, yeah, and then that's how we get. Like,
Okay. So this here is depth, all right? This is width, sorry, this is length. Mhm. And this is
Oh,
width.
yeah, that one, that's.
Okay, so your cross-sectional area is going to be this cross-section here. Okay, so this is A cross. All right, and your A-plane area is going to be the length times the width, which is that one over here. So that's your A-plane. Okay, there's a more accurate diagram drawing in the homework solution, so please take a look there. Anyway, moving forward, I'll try to be quick, I promise. So here we have two things here, the A cross, right? So what is A cross? So A cross is equal to Q over VH. Okay, we found VH here. We know what Q is based on our question. We can find A cross. Okay, so that's the area. So once you have that area, you can calculate the depth and width, or the depth or width. Sometimes they give you a ratio. They tell you like the depth is 1/3 the width, something like that. So you can substitute this here and find the width. Okay, so that's how you do this question. All right, so to find the A-plane, so the A-plane, what is it equal to? It's equal to Q over Vs settling velocity, right? Well, it's equal to Q times Vs. At times, the question might say you have a peak velocity, you have a peak flow rate. You're gonna use the peak flow rate here. Okay, they give you like a peak fraction. They say like Q peak is equal to the normal Q, right? Times the peak fraction. Okay, there's a peak fraction. And this question was, I think, 2.5. Okay, peak factor. Okay. And then usually it's also associated with a safety factor, around maybe 1.5. Okay, so it's going to have a safety factor here, another safety factor value. So good, so far so good. Okay, so to solve this question, you need to know what Vs is. We have all the other parameters except for Vs. So how do you do Vs? Step one. I heard it. Step one, find Vs using Stokes' law. Step two, check the Reynolds number with this value. Okay, if it is less than 1, step 3, use transitional Vs transition.
Wait, I thought that
It's
was
greater than.
Greater of, sorry. If it's greater than 1, use transitional velocity.
If it's less than 1, you can just use VS.
If it's less than 1, just use Vs from the start. Right.
I think
Okay.
it'll be.
Wait, what's VS transitional again?
Vs transitional is the
It's the other.
equation, yeah, the other equation of velocity. That's right. The one that has the drag coefficient, the drag coefficients and things like that.
You use the R to solve for the CD.
Yes, so to solve for, after that, yeah, you use the RE, you probably want to find like the CD values. which you need the RE for. So if the CD is already not given in the question, use the RE from this step here. Okay? It might be given in the question already, so it saves you time to solve. Okay? So once you have that, you have VS, plug it in here, you will have a plane. Okay? Then you know that a plane is equal to length times width. Good. And that's it. Residence time? What is residence time? Yeah. Remember, okay, use units are your best friend, okay? So just do the units. Okay, this is meter cube, this is meter cube per day, right? Cancel, cancel, you have day, time. Okay. So last thing is going to be very quick. So everyone's good here?
What's the VH and A cross?
This VH
that we want between this grit and the.
Yeah, so this VH here is for the A cross. Is the one between the grit and the organic.
So we'll solve for A cross after we get the VH.
You will solve for A cross after you get VH, that's correct.
Okay.
So that's the first thing you do. You solve for V cross using that VH. Because you're gonna okay, I erased it. So VH is going to be a velocity between your what was it, organic?
So it's just arbitrary. You just pick one.
Yeah.
You just
It
pick
just has to be in between.
It has to be in between.
Could like average them.
And then you find the VS using Stokes? What's
The Stokes equation. So the Stokes equation is it's a pretty convoluted so what I would recommend you to do is there's a homework solution. This is homework number 8. So go back to homework number 8 solution, and you will find the Stokes law equation, but you also find the transitional velocity equation. So take a look at both those, and I think I will answer your question there. Okay. The last thing is the Weaver plot. Okay, so for the Weaver plot is basically a method to linearize your data. Okay, it's a plot that is between log Q, all right, and log SE, whatever substrate, log S. Okay, and the reason we write it that way is because your original equation is Q is equal to K C 1 over N. Okay, this can be for the sake of consistency. Okay, so when you want to linearize this, it's going to look like log Q log K, okay, plus 1 over N log C. Okay, so that is actually, I'm thinking of something else, sorry. So it's 1 over U, hang on, I'm sorry.
Log was for.
I got confused with something else, I apologize. So this plot is simply the 1 over U and 1 over S. Okay, 1 over U with 1 over S. It's a method to linearize something. What I want you to remember, because this is not written anywhere, is that whenever you get a straight line, the straight line that comes out of this graph, it has the equation of 1 over U Ks YK 1S plus 1 over YK. Okay, so from this, if there was like a plot in the if there was a plot in the I believe it's the plot is the other way around. If there's a plot in the exam and it tells you, okay, I want you to find Ks and I want you to find U max. Okay, so to find an important point, U max is equal to YK. Okay, U max is equal to Y times K. All right, so you find U max with this. Okay, and then you use this value to find KS. Okay, to find KS by using that U max, because you have this value. Or it can also be your slope.
That is K subscript S or, yeah, okay, yeah, cause
I'm
Is
sorry.
it not,
Yeah, K subscript, the K subscript S. I'm sorry.
Do you not use Umax over two to get to the KS? I just thought I remember seeing that somewhere, but that might just be.
That was for the other plot, I think, that's when it's not when.
Okay, okay.
Then
So-
you-
So the other plot looks something like this.
Yeah.
Okay, with multiple different dots and stuff like that. So this one is U and this is
Yes.
S here. Okay, so to find U, you simply find the maximum value. Okay, that will be your U max, just by observation. What about KS? KS is equal to S when it is U max. Okay.
Oh, yeah.
KS is equal to U max at the maximum at the U max. So if this is your U max, if this is your U max plot or U max point, the S value that's corresponding to it is KS.
I think KS is.
KS over two.
Yeah.
KS. KS is mu max over 2.
It's the S value where you then.
Hmm. But then you have this other equation here that says mu is equal to mu max.
Oh, that's the pseudo first
Yeah,
order
that's
part, so that's this, like, if you
Yeah, at
treat that
the
as like a
beginning.
straight line.
Right.
So at low substrate concentration, it's like pseudo first order.
Oh,
So it'll
yeah,
follow
yeah.
that.
Yeah,
I got you.
I
Okay.
don't think this really.
Okay, gotcha. So, okay. So then just remember that KS is mu max over 2. Okay. You good? Sorry, my brain is frying right now. They're frying too. So we're all on the same boat. Okay, I wish you all the best of luck. So, yeah, and you can do this.
Have you seen the exam?
No. Okay, so practice your homework questions. Practice your homework.
Homework that they go back to.
Just go like press. It's 6 to 12. Yeah, just go over them. Go over the solutions. Go over 6 to 12.
This is disinfectant.
Oh.
Yeah. Okay.
No, he said.
Yeah, he said infection, but.
I think.
He said anything was, that's probably.
Oh.
Yeah. You did ask.
Thank you.
Yeah, you're welcome.
So he did, he might have done this.
Yeah.